has happened in the world of Zen and the world of virtualization in general since then. But FOSDEM was a really good event for Zen 2 years ago. I think when I did the talk, a lot of people hadn't used Zen before, went out and used Zen, but also we got some of the best developers that joined the project actually came about as a result of the talk at FOSDEM 2 years ago. So hopefully we'll have the same effect this year. So what I'm going to do in this talk is just kind of give a bit of a status update of where we are with the Zen project, what the project's goals are, and then look at how the virtualization landscape is evolving. So there are certain things which virtualization was used for a few years ago, and then there's where we are now and where I think things are going to go in the future. So the sort of second generation virtualization benefits, and then really talk about the work that's going on in Zen, within the Zen project to try and bring those, to flesh out that roadmap and bring some of these features into mainline Zen. We'll look a bit at the architecture of Zen and what we regard as the architectural advantages that make Zen really well suited for being, what we call ubiquitous virtualization, so being deployed ubiquitously on hardware. Why we think it's got the best architecture for doing that, and then look at some of the other projects going on, really taking Zen from servers onto client machines and even to mobile phones. So this is the Zen project mission statement. This is actually a slide from the last Zen summit we had, which was in November in Santa Clara. It was actually hosted by Sun. And the aim of the project is to build this open source engine, the open source hypervisor, which is going to be the core engine that then people pick up and put into all sorts of different products that need a hypervisor. So there are lots of different people or different companies that pick Zen up and put it into products. So obviously there's Red Hat and Novell. There's also Sun with Solaris. There's obviously ZenSource, now Citrix, VirtualIron, all sorts of different companies that are building products on top of Zen. So Zen's model is rather like Linux in that it's just building the core. It's not building a final shrink wrap product that you get on a CD. It's just building the engine that then other people turn into products. And the aim is to have that core engine as the sort of industry standard open source hypervisor that everybody develops on and uses. So Zen has always had great performance, and it's certainly the project's mission to make sure that we continue to have industry-leading performance. And the way that we've done that is through these two techniques, and I'll be going into more detail of that later. But we always make sure that we're first to exploit any new features that are added to the hardware, whether it's in the CPU, the chipset, I/O devices like NICs or SCSI host bus adapters or fiber channel host bus adapters. We want to make sure that we take advantage of those features which are added to the hardware. And we actually do a lot of work with hardware vendors to actually tell them what we want to see in the next generation hardware. So that's been one of the cool things about working on the Zen project, is we can actually, we're actually getting stuff into Intel and AMD's CPUs from conversations that we had about 5 or 6 years ago saying we want this feature, and now it's arriving and we're getting exactly what we want. And the same with I/O adapters and things like that, except the turnaround time is much quicker. So we really are getting the kind of hardware support we need to be able to make a really great job of virtualization. And that goes hand in hand with what we've been doing with operating system vendors of getting changes and extensions added into the operating systems to actually make them aware of the fact they're running in a virtualized environment, and that can help you get better performance and also enable more predictable behavior. So now there are a lot of people using Zen. We have a real burden on us to maintain the reputation it has for stability and code quality. And now we really have to think very carefully about what we're doing from a security point of view. Certain other hypervisor companies have had quite a few embarrassments in the last few months of having all sorts of security vulnerabilities, and that's certainly something we want to try and avoid. So we do a lot of work in the Zen project to sort of do a belt and braces approach to security, where you have multiple levels of or domains of security, and really try and have a minimum privilege approach. There's a lot of work ongoing on Zen at the moment to really try and make sure that's the case. We also want to make sure that Zen works from the very big to the very small. So at a couple of Zen summits ago, there were two talks which were back to back. One guy was talking about bringing up Zen on a 4096 processor i64 supercomputer, and then the very next talk was about bringing it up on a Samsung mobile phone. So we really are spanning that whole range of systems, and we'll be looking at some of the reasons why virtualization is interesting on these smaller devices later on. So Zen started off as a university project in the University of Cambridge. Started, I guess depends when you define the start point, but around sort of 2000 and 2001 it started in the university. And we've always wanted to make sure that it has a close connection to research and is very accessible to folks in universities and other research labs, so that they can pick it up, add stuff to it, and really experiment with virtualization. And we've really greatly benefited from that. There are an awful lot of universities, some of the top universities around the world, have research groups which are actively doing stuff on Zen, and Zen benefits hugely from that. We want to make sure that continues. The other thing the Zen project worries about is interoperability, because the dominant hypervisor out there at the moment is obviously VMware's. So we need to make sure that there are tools to enable interoperation between the two. And so there's work being going on to work with VMware to define something called OVF, or Open Virtual Format, which is an open standard for defining virtual machine metadata. And that will hopefully, when everybody gets around to implementing it, means that it will be easy to move virtual machines between the different hypervisors. Even Microsoft has announced they're going to adopt this format. And there are other areas where you need standards as well, such as for when you're adding these paravirtualizations to the operating system, trying to make it easy to do that so that it will work with different hypervisors. So we've been working on things like paravirtops in Linux, which is a way of exposing information about what's going on in the kernel to the hypervisor to get better performance. And that's actually been done in conjunction with VMware. So the Zen community today is doing pretty well. If you look at the 3.x series, which are the most recent series of Zen releases, there have been, I think, something like 250 plus contributors who have submitted substantive patches that have made it into the code base. And if you look at how the Zen community is made up, then you get these different constituent groups. So obviously the main concern of all of the different vendors that that pay people to work on Zen, they're mainly concerned about making Zen work well with their particular products. So obviously Intel and AMD have teams of people working on Zen, helping to ensure that when some new feature is added to the CPU, that support for it is in Zen. They try and get that in so that it's in before the new processor with that feature ships. Zen has already got support for it. So it often ends up being the case that the code in Zen often turns out to be the documentation, effectively, for the new feature that's been added, because it takes these companies ages to actually get all of the documentation signed off so they can actually make it public. So there's been plenty of examples where the documentation has still been top secret, but the code has been in Zen for some number of months. So the other sort of group of vendors that are interested in Zen are obviously operating system vendors, to make sure that they've got the support in their operating systems to make use of the hypercalls that Zen offers to enable them to get best possible performance. So obviously folks like Red Hat, Naval, Sun, they're primarily concerned with making sure that their particular operating systems work well on top of Zen. And then there are all the different management vendors who are more interested in the actual advancing the management APIs. So I said that the research community was very important for Zen, and let's just sort of re-emphasize it here. We have folks which are developing new features for Zen, but I think one of the things which is particularly cool is there are people coming up with whole new use cases for virtualization. So there are some examples of, which I'll be talking about later, of using virtualization to enable mobility of virtual machines between servers and clients, and I think that's going to be pretty interesting. So there are lots of universities, but also quite a few corporate research labs, IBM, HP, Intel, even the NSA have submitted quite a bit of code to Zen. We get the odd bug fix, but they've actually submitted some quite substantial patches to add various security frameworks to Zen. So there's obviously a very large Zen user community, and one of the things which I think is particularly interesting is the fact that companies like Amazon have picked Zen up and have built their elastic compute cloud service on top of Zen. And that's actually the biggest virtualization deployment in the world. It's running on thousands of machines. So although, I guess VMware is perceived as being the market leader in virtualization, if you actually look at some of the biggest virtualization deployments in the world, some of these sort of well-known companies, they all end up running on Zen. And so, I think that's indicative of the fact that Zen actually works really well and has sort of good, is suitable for these enterprise applications. So one of the things that's happened in the last year is we set up zen.org and sort of moved everything that was previously being maintained by all of the websites and so forth by ZenSource is now in this sort of separate zen.org, and there's now a Zen advisory board made up of some of the major code contributors to Zen to sort of provide management oversight of the project and all things like that. So now if we look at some of the uses for virtualization and see how that's evolving over time. So the first use case for virtualization was really around server consolidation. So the pretty obvious thing of running multiple virtual machines all on the same machine. And the reason this was so interesting is because of something which, when I got involved in the project, I didn't really realize was happening. But the way that most companies organize their IT infrastructure is they have this model of having one operating system image running one application. You don't try and put multiple applications into the same operating system because you get all sorts of configuration interactions, obviously particularly in the Windows world. Plus also, it's often the case that the application vendor won't even support their application if it's running alongside something else. So I guess this is less prevalent in the Unix world, but it's very much the case in the Windows world. And obviously most applications are running on Windows. So the net result is that a company it just ends up having to buy more and more servers. Like, people are suffering from what's called server sprawl. And there are some companies I've visited, like large Wall Street banks, where they actually have a lorry turn up every week and just unload pallets full of servers, because that's the rate that they're consuming new servers. They have to build a new data center every year to house another 10,000 machines. And it's just completely crazy. If you look at the utilization of these machines, you typically find the typical CPU utilization is somewhere between 5 and 10%. And it gets worse every year, because as fast as processors come out with things like multi-core as well, each individual application's typically able to use even less of the machine. So as a result, consolidating different virtual machines onto the same server provides a lot of benefit. Another reason that people have been using virtualization is just for improving manageability. If you think about it, if you're trying to build a lights-out server room, it's actually pretty tricky today if you're doing it with physical hardware, because there really aren't good standards for doing things like power cycling servers, connecting to the console, and things like that. You often end up buying external boxes to do it, because if you try and use the facilities built into the servers. There's just not good standards between Dell and HP. Nothing really particularly interoperates like at that level at the moment. Whereas if you just put virtualization on everything, you've then got a standard and secure interface for connecting to the consoles, rebooting the virtual machines, and so forth. The other advantage you've got is it's very easy to deploy new images on a given, when it's on virtualized hardware. It's quite tough to do when you're doing it on physical hardware, because you've got to make sure that you've got all of the right drivers for the particular machine you're deploying it on. But in a virtualized world, you can have a single image and then just bring it up on some large, on any of the server plant that you've got. And that's also useful for doing things like disaster recovery, because it means that you can have another site and you don't have to have an exact identical copy of the hardware on the other site. You can have different hardware but still be able to bring those virtual machine images up on those on the machines at the other site. Also, one of the things which I didn't realize before I got involved with this this whole Zen stuff is quite how much old versions of operating systems there are out there. Even if you look at in the Linux world, if you look at what versions of Linux are actually out there in number and in use in commercial applications, it will be much older than you think. So we've come across banks where they have 15,000 machines running Linux 2.4 kernels as from RHEL 3, and then they're just beginning their migration to RHEL 4. And not at all interested in RHEL 5 yet, because until it's been out there for 3 or 4 years, it's unproven. The bugs haven't been shaken out. So that's a real problem for them with all of this sort of legacy operating system versions, because none of them will boot on modern machines. They just don't have the right drivers or the right CPU detection. So that's obviously a big issue, and virtualization can help you solve that by providing this virtualized platform that enables you to run even legacy operating system instances. So if we look at some of the second generation virtualization benefits, obviously you can use techniques such as live relocation, where you can actually move a running VM and all of the applications within it to a different physical server without actually interrupting the application and operating system while you're doing so. Typically, the downtime when you're switching over between the two machines is typically the order of 100, 150 milliseconds, something like that. And the way that that works is that you start this process where you're synchronizing the memory between the two machines, between the physical machine where the VM is currently running, and the machine where you're going to be moving it to. So you're copying the memory pages across, but noting which pages have been updated since you last copied them on the machine where it's actually running. And then you go back and copy those. And you just do that process iteratively until the amount of the number of pages of memory which have yet to be copied is small. And typically when it's just a few hundred pages, you'll then stop the virtual machine, copy those remaining pages across, and then copy across the state of all of the registers in the CPUs, the devices and things like that. That will all get transferred across. You check everything has arrived safely, and then you kill the virtual machine on the original host and unpause it on the new host, and it will just carry on as before. And because that virtual machine, because you'll have migrated the MAC address of all of the virtual network interfaces and so forth with it, what will happen is the first packet that virtual machine sends will cause the Ethernet switches to reconfigure and then divert all traffic to that location. So you really do get seamless, or near seamless anyway, movement of virtual machines between physical hosts, and you can use that for a number of different uses. So one is that if you know a machine is about to fail because you've just had some IPMI warning telling you the fan is about to fail, or a smart warning telling you the hard disk is about to fail, or you just want to perform maintenance on the server, you can evacuate all of the virtual machines off it onto other servers, and then just take the machine down for maintenance. And similarly, you can use this VM relocation for performing rebalancing of workload across a set of physical machines. So if you've got 3 VMs running on one machine, and you detect that they're overloaded, you can move one of those VMs to another machine. So this kind of capability is particularly interesting to companies like hosting providers, or in fact anybody who's just got a set of virtual machines that they want to run on a pool of physical hardware, and they want to move the virtual machines around to maximize the performance that each of the OS images gets. But in the hosting provider case, it was really one of the main drivers for Xen, because if you think about it, if you had a hosting provider with a single machine might chop it up, say, into 10 and sell it to 10 different customers. And then if they had 10 machines, obviously they could sell these 10 machines to 100 customers. But as soon as you start having the ability to move the workload around, you can actually add more customers, but arrange that the ones that are actually using their virtual machine at any one time are on different physical hosts. You can actually add in more customers, and the sort of satisfaction that the customers have with the service remains unchanged. And so, some hosting providers found that rather than selling 10 machines to 100 customers, they were able to sell it to 200 customers, and the customers would be equally happy, and they'd be making twice as much money. So that was really, one of the main drivers for Xen's wide deployment by hosting providers. So one of the other interesting things you can do is to enforce security policy. So you have this situation today where you're really reliant on the administrator inside each of those given virtual machines to actually have configured the virtual machine properly, to make sure that things like the firewall is set up, but they're remembering to back up all of the stuff within the operating system, etc. But one of the cool things you can do with virtualization is to actually enforce some of this stuff external to the given virtual machine. So you can actually implement a firewall within the virtualization layer. So it doesn't matter if each individual virtual machine has it configured correctly, because you can actually do that defense on their behalf. If you think about it, it's like taking an external firewall that you might have at the edge of your organization, and then bringing it inside and putting it directly in front of each virtual machine, actually implementing it as part of the virtualization platform. And not only can you do that with things like security, with things like firewalls, you can actually do things like virus scanning on behalf of all of the virtual machines as well. So you don't need a copy of Norton or whatever inside each of your Windows VMs. You can actually just have one copy and then scan all of them. And also, things like that tend to work better, because obviously the first thing that any virus or Trojan is going to do if it gets inside a virtual machine is to disable the virus scanner. Whereas if you're doing it outside of the VM, looking inside it, you can actually avoid those kind of things from happening. Some other things which I'll talk a little bit about later, we've actually done some work to detect when it looks like virtual machines may have been compromised. So we can actually provide some facilities which provide better security for operating systems when they're running in the virtual world than they would actually get in the physical world. So one example is this idea of having immutable memory. So the idea is that for areas of the, say, a Linux kernel or a Windows kernel, you know that after the OS has been loaded, they should never change. So things like the system call table and all of the kernel code really oughtn't to be changing after the VM is booted. So what the VM can do is register that memory and irrevocably give up write access to that memory. So no matter how hard it tries, it will never be able to update those physical pages. And so it just tells that to the hypervisor, which then enforces it. So the cool thing about that is that when your rootkit tries to install inside the VM and start patching all of these things, it will try writing to these areas of memory which are immutable, and you'll catch that, and you can then suspend the VM, put it into quarantine, and then go and poke it with a stick later. So I've gone through some of these benefits of this is just putting it in textual form, but the idea of rather than just having one hypervisor, of having a pool of machines running running Zen or running a hypervisor, and then making use of the fact that you can have a pool of virtual machines running above the pool of physical hardware, and you've got flexibility about how you map and move those virtual machines around between the hardware. How you can enforce administrative policy for things like backup, firewalls, virus scanning. And also another thing which is quite cool is the fact that you can abstract the physical world complexity. So this virtual machine can think it's just got a simple IDE or SCSI disk inside it, whereas actually that disk might be some complex, raided disk with multi-path configurations to get to the disk. And rather than having to expose all of that real, horrid, nasty complexity of the physical world to each administrator of each virtual machine, they just see a single, simple disk that is actually backed by this much more complex physical setup. So some of the other things that virtualization enables is it actually simplifies application certification, which is something which turns out to be really important in commercial computing, is that the given application has been certified on a given operating system, and that operating system is certified on a given piece of hardware. And by separating that out to having the application certified on the operating system certified on the hypervisor, and then the hypervisor on the hardware, although you end up with more steps, it actually makes things easier for the application vendor, because they can pick a given operating system they want to certify their app on, and then everything else is taken care for them. So rather than having to worry about certifying on several different operating systems, all different versions, or Windows and Linux, they can just pick one and then know it's going to work. So I think this is actually going to be quite important for increasing the take-up of use of operating system, open source operating systems like Linux, because the vendor can just pick the one they want to support and then know it's going to be available everywhere. They can actually ship a virtual appliance containing the application already installed in the operating system and know that it's been configured and set up correctly. So I think this is going to be a very common way of packaging software in future, where you ship the application already installed inside the operating system instance. And I think that's going to be very good for open source operating systems. So second generation virtualization has excellent performance, and that's really been brought about by using these facilities that have been added to the hardware and operating system power virtualization. So if we sort of look in more detail at that. So multi-core processors, meaning that now pretty much every server you buy, or each CPU, is going to have at least 4 cores, and you'll typically have 1, 2, or 4 sockets. And one of the things which is interesting in Intel's next generation processor architecture called Neolim, hyperthreading makes a comeback. So as well as having the 4 cores, you're going to have 2 threads on each core. So you're going to have effectively 8 CPUs, or at least as exposed to software, within each socket, and then maybe 16, even a pretty basic 2-socket server. And the fact is that most operating systems and applications haven't really caught up with that. There are plenty of applications which are still single-threaded, and certainly plenty of operating systems, if you start doing heavy I/O, start showing real scalability issues when you get much above 4 CPUs. So virtualization is a really good way of just chopping up physical systems into a number of smaller ones and enabling you to run existing applications and operating systems on them. So there have been a number of times where we've seen some surprising results, because you wouldn't expect virtualization to ever improve performance. If you're talking about total throughput of a system, because there's always going to be adding some amount of overhead, hopefully a small amount of overhead. But we've seen plenty of instances where somebody had been running one application, say on a 4 CPU machine, and they found that they got rather better throughput if they ran Zen on that machine, created 4 uniprocessor instances, 4 uniprocessor VMs, and then ran a copy of the application in each. And the total throughput that they got was rather better than just running a single instance, because the application didn't have the SMP scalability that was necessary. But even things that you would expect to scale well often don't. We've seen things like that happen with Apache, where you can actually get better performance running multiple web servers, each in their own OS, rather than running one on a big machine. So obviously Zen makes use of Intel VT and AMD's AMD-V. There are other new hardware features which are emerging within the CPUs, such as nested paging support. And Intel call this EPT, AMD call it VMI. And this avoids us having to use a technique called shadow page tables. One of the biggest challenges of virtualizing the x86 is dealing with virtualizing the memory management unit. And what you have to do is to effectively, when the guest writes to pages which contain page table information, in general, those pages which it's writing to, thinking of page tables, are not the page tables which are actually used by the processor. And so what you have to do is you have your own copy of those pages called a shadow page table, and you have to keep the two in sync. So when the guest updates an entry, you have to make sure you update that entry in the shadow. But then as the processor runs, it's making changes into the shadow too to update things like accessed and dirty bits. And you have to propagate that information back to the guest page table. Otherwise, bad things happen. Like if you don't propagate a dirty bit, Linux will think a page isn't dirty and won't bother writing it out to disk when it swaps it. It'll be able to just throw it away. So this is a really tough challenge, implementing the shadow page table algorithm to get good performance, yet maintain the right, maintain the integrity. So I think we're rewriting the shadow page table algorithm in Zen for the 6th time at the moment. And we get better and better each time. And we're now at the point where, we're doing a much better job than we really thought we would be able to a few years ago. But now all of the hardware vendors are adding support to make the shadow, or to actually avoid having to use shadow page tables. So the hardware will actually do this translation of virtual addresses into what are called guest physical addresses, because the guest thinks it owns the physical memory of the machine, but it doesn't really. But then there's another layer of translation into real machine physical addresses, which is where the memory that's actually being used. And the hardware will do that for you. So now there's this competition going on to see which works better, using the hardware support or using shadow page tables. It's pretty neck and neck at the moment. AMD are shipping these chips that have VMI support. And so Zen's shadow page tables, you actually want it turned on for some benchmarks, and other benchmarks you want to let the hardware do it. So there's an interesting thing going on of trying to choose dynamically, depending on the workload, whether to do it in software or hardware. And that's key with many of these things. You actually want, you can't solve the whole problem in hardware. You can't solve the whole problem in software. You really want to pick the best features of both to come up with the ultimate solution. So the other big load of work that's happening in Zen is taking advantage of I/O devices which have been designed with virtualization in mind. And I'll talk a little bit more about that in a later slide. So the other big thing that helps us get good performance is the changes that have been made to the operating systems to make the job of virtualizing them easier. And so, when we sort of came up with these techniques, we called it OS paravirtualization. That was when it was a research project in the university. The marketing term, which seems to now have been adopted by most companies, is OS enlightenment. So that's what it means if you hear that term. So the idea here is just, it goes hand in hand with this hardware virtualization assistance that's being added to the CPUs, etc. But by using the two together, you can get better performance. So just to give an example, let's just take that back. If you're on a SMP system, or you're supporting SMP guests, as Zen has done for a long time, you can add facilities to the operating system to tell the hypervisor about various events, which are quite common on SMP systems. Supposing you want to flush the TLB, or supposing you've updated the page table for some particular process, you then need to make sure that all of the CPUs flush their TLBs or flush certain entries in the TLB so they can synchronize against this new page table. If you're trying to do that purely with hardware, emulation of what would happen on a physical system, it's incredibly complicated, because the CPU that decides it wants to do the flush is going to have to talk to the APIC, the local APIC, to try and send IPIs to all of the other CPUs, which will then try and flush their TLBs. Whereas if you're running on a hypervisor, you can just call down to the hypervisor, you can make a hypercall saying, please flush the following page table on the following list of CPUs. And then the hypervisor can just do that in one go. And you'll be talking about a few thousand cycles instead of 50, 100,000 cycles if you try and do it through emulation. In fact, realistically, it's probably something like several 100,000 cycles. And the good news is that these OS enlightenments or power virtualization extensions have been adopted by every commercial OS vendor and many non-commercial ones like NetBSD, FreeBSD, etc. All of those power virtualization extensions are available for those OSs, and as a result, you get much better performance when running on Zen. So even Microsoft have adopted enlightenments or power virtualization. So Windows 2008 can detect that it's running on a hypervisor, and then will make hypercalls for when it wants to do some of these things. It really doesn't make make use of many of these hypercalls at the moment, but presumably in future releases they'll get better at it. So Zen is a true hypervisor design. So if you look back to, there was a lot of work done in virtualization in the 60s and 70s. And IBM came up with this term hypervisor, and it really meant a thin layer of software that was the most privileged layer of software in the whole system. And you just do the bare minimum in that layer to virtualize the CPU and memory management, interrupts, timers and things like that, and try and push everything else outside. And that's exactly what Zen does. You try and do as much as possible outside of that core trusted piece of code. And if you implement everything else in the way we try and do it in Zen, is actually running those facilities in other virtual machines. Because the virtual machines can be very lightweight. We have some virtual machines running on Zen that are based on something called mini-OS, which is kind of like a minimal OS implementation that runs as a Zen domain. They can just be a few 100K in size and can provide services on behalf of other guests. So the idea is by pushing all of this outside of the hypervisor, it improves or better enables you to maintain security. It also enables you to have very efficient scalability to very large SMP systems, because you haven't got one operating system image that's having to see all of the processes, as you would have in, say, a hosted hypervisor or a hosted virtualization environment, where you have one host operating system that sees the entire machine, all of the CPUs, all of the memory. On Zen, we just don't have that problem. There's only the hypervisor, which is this very thin layer, sees the whole machine. And by having this small, trusted computing base, it's definitely good from a security point of view. So there's a lot of work in Zen at the moment to further deprivilege the system and to break services out into these service partitions to improve security. And actually, every time we do that, it tends to improve performance as well. The other advantage Zen has got is that it's completely operating system agnostic. It doesn't have to use Linux or any other OS for the control plane. And so, I think that for where we want to take Zen, it's very important that we are platform agnostic or OS agnostic. So anyway, if we look at where Zen is going, we've got various things coming together. So the overhead of virtualization is getting smaller via this hardware assistance and through power virtualization. The net result is we're going to end up with near zero overhead, particularly when these smart I/O devices are ubiquitously available. So we believe that virtualization is going to be always on. That you will, in a few years' time, actually wouldn't dream of running an operating system on bare metal again. You'll just have, when you buy a machine, it will have a hypervisor installed upon it, and then you'll just be instantiating virtual machine images on it. If you think about it, that's how it was in the days of the mainframe. I think it's how it's going to be on PC hardware in the not too distant future. So Zen's goal has been to architect itself to be this best choice for ubiquitous virtualization. And we're actually seeing that happen. Just later on this year, a number of the top tier operating system vendor or top tier hardware vendors are actually going to be shipping servers where having Zen embedded in the firmware of that server is actually an option. So when you're buying your server, you select Zen, and Zen will come embedded in Flash on that server. And I really think that that is the way things are going to go, that we're going to end up with the hypervisor just built in, part of the platform. And then you just instantiate operating system images on top. So I think it's really cool that we're getting GPL code out there, hopefully on every machine that's leaving the factory. Hopefully people will select that Zen option, and we'll really get this huge uptake in GPL software out there in the wild. So if we look at where we're going with Zen server, with Zen roadmap for servers, there's obviously a lot of work around always improving the performance and scalability. One other thing which is interesting is now that Microsoft have made the spec for Windows 2008 more open, we can actually natively implement the hypercalls which Hyper-V has to enable Windows 2008 to run paravirtualized on Zen. So obviously the aim is to do a better job of running Windows than Microsoft. So let's just skip some of these slides. So one of the things which is happening is Zen is moving from the server world through to clients. So I think what we want to do is to make a really good job of getting Zen running on laptops. So you'll be able to have VMs that provide improved security and manageability for client systems, and also be able to have things like instant on VMs for accessing web browsers and email, that when you turn the machine on, the hypervisor will just boot in a few seconds, and then you can actually switch between different VMs. So you might have a dedicated VM for web browsing, so you wouldn't have to wait for Windows to boot on a client. You could just access this, if you just wanted to do some specific functions, you could use these inbuilt instant on VMs. And there's a whole load of work that we need to do to better support that, such as passing things like the graphics device directly through into guests, so that we can actually make use of all of the 3D hardware. So I talked a little bit about mobile phones. There's this work done by Samsung to get Windows running, to get Zen running on these ARM-based mobile phones, where you have 3 VMs, 1 VM for controlling the radio, 1 VM for running all of the vendor-supplied software, and then another VM for running anything you download. So you can download basically any junk to the phone, but you'll still be able to make emergency calls. So one of the other, just finally, project I want to highlight is this very cool thing that's happening on Zen to enable Zen to have hardware fault-tolerant VMs, where you run 2 VMs on 2 physical machines in lockstep. So rather than just doing this process of live relocation, so when you plan to move a VM from one physical node to another. In this mode of operation, you'd be running the 2 VMs in lockstep, so that you could walk up to one of the machines, just pull the power plug out, and the VM would just carry on running on the other machine. So the net result is there'd be no downtime at all, and you'd then be able to tolerate hardware failures. And of course, you could just rather than just having one virtual machine, you could have, or 2 virtual machines in lockstep. You could have more if you wanted to be able to tolerate more failures. It also looks like you could locate these virtual machines some distance apart, depending on the application. Some applications are a bit sensitive to how close they are, but you could certainly some of the banks are interested in having one virtual machine running in New Jersey and one in Manhattan, connected together, so that if something bad happens to one of their sites, all of their applications just seamlessly carry on running at the other site. And there's this project called Remus, which has been doing exactly that on top of Zen. And obviously we want to get these kind of facilities back into mainline Zen. And there's a lot of interesting discussion about the techniques that are being used, whether you're continuously checkpointing the VM and transferring the state to the other location, or whether you're running the VMs in lockstep using what's called deterministic replay techniques. There's a lot of really cool stuff that's being done on Zen here. So anyway, conclusion of this talk, I think Zen is really coming of age. It's becoming a key platform component. We're going to see it widely embedded in server firmware. And we've really, we think the work has paid off of architecting Zen for this ubiquitous virtualization. And we believe that it's going to become a reality in a few years' time. So now I think the interesting challenges are getting Zen as pervasive on clients as it is on servers, and then ultimately down to mobile phones. So if you want to get involved with the Zen project, then you can download and play with Zen, look at the source code, etc., from zen.org. If you just want to actually sort of use Zen in a simple deployment and don't want to figure out how to set it all up, then I'll just briefly plug ZenSource's Zen Server Express, which is kind of like a single CD that you put in the machine and install it, if you don't want to mess about configuring things yourself. So anyway, thanks for listening. I guess there are a couple of minutes of questions. 2 minutes. Hi.
Hi, you mentioned running the VM on separate machines for failover. What benefits does that give compared to what we do today, where you would have one machine failing over to another anyway? What's the VM doing that it's adding value to what we would do with DRBD and heartbeats today?
Right. Well, the key thing there is that when you do the failover, you've got to wait while you reboot, boot another instance of that application, and then it's got to run, FOSDEM or do its own internal consistency checking, and then the application will be up and running at this new location. So you're going to be looking at a downtime of at least tens of seconds, if not a couple of minutes, for something like a database while it sorts itself out. What we're talking about with this fault-tolerant stuff here is running 2 virtual machines in lockstep. So when it fails over to the other machine, the entire state of the application, if you're logged into this machine, you can be SSH'd in, pull the plug out of the machine, and you're still SSH'd in on this other machine. So it's the entire state has failed over, not just the copy of the disk image.
So there's a state transfer protocol.
Yeah, that's occurring all of the time, making sure that the 2 VMs are in lockstep. Yeah, so Zen Scheduler enables you to set weights and caps. So you can say, I want this virtual machine to have 10 times more resource than this one, or I want to limit this virtual machine to have no more than 500, 50 milliseconds of CPU every 200 milliseconds. So yeah, you can do some of that scheduling for I/O as well. So I'll just answer this question. We are actually out of time, but so virtualization doesn't improve performance in general, right? It's adding overhead, but the overhead is getting smaller and smaller. So for something like networking is one of the hardest things to virtualize, because if you think about it, a packet arrives on the machine. You've then got to determine which virtual machine you're going to deliver it to, and you typically have to copy that packet. So there's an extra copy that you have to generally do to virtualize the network. But we've been working with network card vendors to actually encourage them to build smarter hardware that we can push information down to the card so that when a packet arrives, it can already demultiplex it to the virtual machine that's going to receive it, so you don't have to do that copy. And so there are now a whole bunch of different network card vendors, SolarFlare, Broadcom, Intel, Chelsea, that are all building network cards, which when running in a virtualized environment will deliver the packet directly to the VM. And we're actually seeing that, say, in the case of the SolarFlare card, you can get line rate 10 gigabit per second networking into a virtual machine, exactly, or within a couple of percent of what you would get into a physical machine running on bare metal. So I really think the overhead of networking has pretty much been solved if you're using this modern hardware. Okay, thanks. Sorry, just come up later.